Right now, somewhere beyond Earth's atmosphere, the fastest object humanity has ever created is moving through space at over 430,000 miles per hour. At this velocity, you could circle the entire planet in less than 4 minutes. Yet this same spacecraft, traveling at a speed that would instantly vaporize anything it collided with, would still require more than 6,000 years to reach the nearest star beyond our Sun. This single fact reveals something profound about the nature of space travel that most people never fully grasp. The distance a human could actually cross in a single lifetime is not limited by engineering capabilities, available funding, or human determination. It is constrained by something far more fundamental, woven directly into the structure of reality itself. But within this constraint lies a mechanism so remarkable that it could theoretically allow a traveler to reach destinations millions of light years away while aging only a few decades. If you're curious about the actual limits of human space exploration and the science that defines them, consider subscribing and liking this video. It helps more than you might expect. Let's explore what the laws of physics actually permit. The Parker Solar Probe, launched in 2018, currently holds the record as the fastest human-made object ever to move through space. During its closest approaches to the Sun, this spacecraft exceeds speeds of 430,000 miles per hour. To understand this velocity in more familiar terms, at this speed the probe could cross the entire continental United States in under 25 seconds. Standing in New York, you could blink twice and the spacecraft would have already passed Los Angeles, continued over the Pacific Ocean, and be approaching Hawaii. This achievement represents decades of technological development, billions of dollars in investment, and the combined expertise of thousands of scientists and engineers. The Parker Solar Probe accomplishes this extraordinary speed through a series of gravitational assists from Venus, using each flyby to steal a tiny fraction of the planet's orbital energy and gradually build velocity over years of careful trajectory adjustments. This represents humanity's single greatest effort at achieving high velocity through the cosmic void. To appreciate how remarkable this speed truly is, consider the entire history of human velocity achievements. For most of our existence as a species, the fastest any human could travel was roughly 25 miles per hour, the top speed of a running horse. This limit persisted for over 200,000 years. By 1900, automobiles pushed past 60 miles per hour. The Wright brothers flew at 34 miles per hour in 1903. Within 60 years, test pilots broke the sound barrier at 761 miles per hour. By 1969, Apollo astronauts returning from the moon reached nearly 25,000 miles per hour, the fastest any human has ever traveled. The Parker Solar Probe moves roughly 17 times faster than those Apollo astronauts. Yet even this extraordinary velocity reveals something sobering about cosmic distances. At 430,000 miles per hour, the Parker Solar Probe would require approximately 6,600 years to reach Proxima Centauri, our nearest stellar neighbor, located just 4.24 light-years away. To put this in perspective, a journey beginning when ancient Sumerians first invented writing would only now be approaching its destination. A human lifetime spans roughly 80 years on average. This means that traveling at humanity's current maximum speed, you could cover barely more than 1% of the distance to the closest star before your life ended. The mathematics become even more striking when you consider what one human lifetime actually accomplishes at these record-breaking speeds. Traveling continuously at the Parker Solar Probe's peak velocity for 80 years would carry you approximately 3 trillion miles. This sounds vast until you measure it against true cosmic distances. 3 trillion miles equals roughly 0.05 light-years. The nearest star system sits more than 80 times farther away than what an entire human lifetime at maximum velocity could cover. The Oort cloud provides another reference point for understanding these scales. This spherical shell of frozen comets marks the outermost boundary of our Sun's gravitational influence, extending up to 100,000 astronomical units from the Sun, with 1 astronomical unit being the Earth-Sun distance of roughly 93 million miles. The Oort cloud represents the true edge of our solar system, the point where the Sun's gravity finally weakens and interstellar space truly begins. At humanity's current maximum speed, Reaching even the inner edge of the Oort cloud would require approximately 600 years of continuous travel. An entire human lifetime at unprecedented velocities would not even escape our solar system's sphere of gravitational dominance. Consider the Voyager 1 spacecraft for additional perspective on what decades of space travel actually accomplish. This probe has traveled farther from Earth than any other human-made object in history. After more than 47 years of continuous journey through space, Voyager 1 has covered approximately 15 billion miles. This distance took nearly half a century to achieve. Voyager 1 crossed the heliopause in 2012, officially entering interstellar space. This boundary marks where the Sun's solar wind loses its influence against the pressure of the interstellar medium, the thin gas and dust filling the space between stars. Headlines proclaimed that Voyager had left the solar system. Technically accurate in one sense, but misleading in another. The probe escaped the Sun's magnetic influence but remains firmly within the Sun's gravitational domain. It will not pass beyond the Oort cloud for another 30,000 years. 15 billion miles sounds impressive until you realize it represents less than 0.03% of the distance to the nearest star. If the journey to Proxima Centauri was scaled down to a cross-country road trip from New York to Los Angeles, approximately 2,800 miles of highway, Voyager 1 would have traveled roughly 100 feet in 47 years. You would still be standing in your driveway, barely past the mailbox, after half a century of continuous driving. In the time it took you to read this far, light traveled far enough to circle Earth 7 times. Voyager 1, after nearly 5 decades of travel, has covered a distance that light crosses in approximately 20 hours. The probe's 47-year journey equals less than 1 day of light travel. Voyager 1 travels at approximately 38,000 miles per hour relative to the Sun. At this speed, the probe would need over 70,000 years to reach Proxima Centauri. The probe will not survive that journey. Voyager 1 carries a plutonium power source that generates electricity through radioactive decay. This power source loses approximately 4 watts per year as the plutonium depletes. By 2025, the probe will lack sufficient power to operate any scientific instruments. By 2036, it will fall silent entirely, continuing its journey as an unpowered artifact tumbling through the void. The fundamental problem lies in the physics of chemical propulsion. Every rocket humanity has ever launched operates on the same basic principle. Hot gas expelled from one end pushes the vehicle in the opposite direction. You throw mass backward and the reaction force pushes you forward. Simple and elegant, but devastatingly limited for interstellar travel. Chemical rockets face an insurmountable barrier encoded in the Tsiolkovsky rocket equation. This mathematical relationship, derived by Russian scientist Konstantin Tsiolkovsky in 1903, governs the maximum velocity any rocket can achieve based on 2 factors: the exhaust velocity of its propellant, and the ratio between the rocket's initial mass including all fuel, and its final mass after burning that fuel. For chemical propellants, exhaust velocities max out around 4.5 kilometers per second. This is not an engineering limitation awaiting a clever solution. It is a fundamental constraint imposed by chemistry itself. When you burn hydrogen and oxygen, the most energetic chemical reaction we can practically use for rockets, the resulting steam molecules can only move so fast. The energy released by breaking and forming chemical bonds has an absolute ceiling. To accelerate even a small probe weighing 1,000 kilograms to 1% of light speed using chemical rockets, you would need a starting fuel mass exceeding the total mass of the observable universe. This is not hyperbole. This is what the mathematics actually demand. The rocket equation contains an exponential function that punishes any attempt to reach high velocities with chemical propulsion. Gravity assists provide some relief from this limitation, allowing spacecraft to steal energy from planets without burning fuel. By carefully timing flybys of massive bodies, a spacecraft can exchange momentum with planets, gradually accumulating speed. The Voyager probes used this technique extensively, bouncing from Jupiter to Saturn to build velocities that carried them toward interstellar space. The Parker Solar Probe exploits multiple Venus flybys to accelerate toward its record-breaking speeds. Yet even gravity assists have hard limits. The solar system contains only so many massive bodies positioned to provide useful acceleration. A spacecraft designed to optimize gravity assists over decades might eventually reach velocities approaching 150,000 miles per hour, still hopelessly inadequate for interstellar travel within any human timeframe. Ion propulsion systems offer marginal improvements over chemical rockets by dramatically increasing exhaust velocity. These engines work by ionizing a propellant, typically xenon gas, and accelerating the resulting charged particles through electric fields. The ions exit the engine at velocities 10 to 20 times higher than chemical exhaust. The Dawn spacecraft used ion propulsion to explore the asteroid belt, becoming the first mission to orbit two different celestial bodies beyond Earth. Yet ion engines produce thrust so minuscule that their advantages evaporate for rapid acceleration. Dawn's ion drive generated approximately 90 millinewtons of force. To understand how small this is, the weight of a single sheet of paper pressing on your palm equals roughly the thrust of an ion engine. Even with unlimited fuel and a century of continuous operation, ion propulsion cannot approach the speeds necessary for interstellar travel within human time scales. Nuclear thermal rockets represent the next step. These engines work by passing hydrogen propellant through a nuclear reactor, heating it to extreme temperatures before expelling it through a nozzle. The nuclear heat source allows hydrogen to reach velocities roughly twice those possible with chemical combustion, dramatically improving the rocket equation's mathematics. NASA tested nuclear thermal rockets extensively during the NERVA program throughout the 1960s and early 1970s. Engineers conducted dozens of successful reactor tests, demonstrating that nuclear thermal propulsion works reliably. The technology was mature enough for deployment before political and budgetary considerations ended the program in 1973. A nuclear thermal rocket could theoretically accelerate a spacecraft to approximately 100,000 miles per hour with reasonable fuel ratios. The journey time to Proxima Centauri at this speed would drop to approximately 28,000 years. Still impossibly long, but progress nonetheless. Solar sails represent perhaps the most elegant propulsion concept, exploiting the radiation pressure of sunlight itself to accelerate spacecraft without carrying any fuel whatsoever. When photons strike a reflective surface, they transfer tiny amounts of momentum. The Japanese Ikaros spacecraft demonstrated solar sail technology in 2010, successfully unfurling a 14-meter membrane and achieving measurable acceleration from sunlight alone. Close to the Sun, where radiation intensity reaches its peak, a solar sail could theoretically accelerate at rates approaching 1% of Earth's surface gravity. As the sail moves away from the Sun, radiation intensity drops with the square of distance. A solar sail launched from a close solar approach might reach velocities of several 100,000 miles per hour before radiation pressure becomes too weak. At 500,000 miles per hour, the journey to the nearest star would still require over 5,000 years. This is the reality of current and near-future propulsion technology. The fastest speeds achievable through any mechanism humanity has demonstrated, tested, or could plausibly construct within the next century cannot carry a human being beyond our immediate cosmic neighborhood within their natural lifespan. Chemical rockets are fundamentally incapable. Ion engines are too weak. Nuclear thermal rockets help, but not nearly enough. Solar sails cannot accelerate large masses to sufficient velocities. Many 20th century physicists considered travel between stars to be physically impossible for biological beings. The energy requirements seemed astronomical. The journey times exceeded any reasonable definition of practical. The vast empty distances between stars appeared designed to prevent the movement of life from one stellar system to another. Yet hidden within the very equations that seem to imprison humanity lies a mechanism so profound that it transforms everything about the relationship between distance, time, and the limits of human exploration. This mechanism was discovered in 1905 by a 26-year-old patent clerk working in Bern, Switzerland. Albert Einstein asked a simple question: what would happen if you could ride alongside a beam of light? The answers he found contradicted everything human intuition suggested about motion, time, and distance. They revealed that distance and time are not the fixed quantities that everyday experience suggests. They are flexible. They stretch and compress depending on how fast you move through space. A clock aboard a speeding spacecraft does not tick at the same rate as a clock left behind on Earth. In 1905, Einstein submitted a paper to a German physics journal. The paper bore an unassuming title that gave no hint of its revolutionary contents, On the Electrodynamics of Moving Bodies. It contained no complex mathematics beyond algebra. It referenced almost no previous scientific literature. Yet this single document would demolish 3 centuries of assumptions about how the universe operates. Einstein began with a premise so simple it seemed almost trivial. The speed of light in a vacuum remains constant for all observers regardless of how fast those observers are moving. Whether you stand still on Earth or race through space at half the speed of light, you will always measure light traveling at exactly 186,282 miles per second. From this single premise, Einstein derived consequences that shattered intuition. If the speed of light must remain constant for all observers, then something else must give. That something turned out to be time itself. Clocks aboard moving vessels tick slower than identical clocks remaining stationary. This effect, called time dilation, seemed absurd when first proposed. Yet the mathematics proved inescapable, and within decades experiments confirmed what Einstein had derived from pure logic. Time dilation is real, measurable, and it transforms everything about the limits of human exploration. The relationship between velocity and time dilation follows a precise mathematical formula. Physicists use a quantity called gamma, the Lorentz factor. This number tells you exactly how much time slows down at any given velocity. At everyday velocities, gamma barely differs from 1. A car traveling at highway speed experiences time dilation so minuscule that the most precise atomic clocks can barely detect it. The effect becomes significant when velocity climbs toward a substantial fraction of light speed. At 50% of light speed, gamma reaches 1.15. Time aboard the spacecraft passes about 15% slower than time on Earth. 1 year of ship time corresponds to roughly 14 months of Earth time. At 90% of light speed, gamma jumps to approximately 2.3. For every year that passes aboard the speeding vessel, 2 years and 4 months pass on Earth. A 50-year journey at this velocity would see the traveler age 50 years while Earth aged 115 years. At 99% of light speed, gamma reaches 7.1. 7 years pass on Earth for every year experienced by the traveler. A decade of ship time corresponds to 71 years of Earth time. At 99.9% of light speed, gamma exceeds 22. 22 years of Earth time compress into a single year aboard the spacecraft. 50 years of travel would span 1,100 years of Earth history. At 99.99%, gamma exceeds 70. At 99.999%, gamma surpasses 223. Each additional 9 added to the velocity pushes the time dilation factor higher by roughly a factor of 3. These numbers transform the question of interstellar travel. Consider a journey to Vega, one of the brightest stars in our night sky, located approximately 25 light-years from Earth. At conventional spacecraft velocities, reaching Vega would require hundreds of thousands of years. At 99% of light speed, with gamma at 7.1, the calculation transforms completely. From Earth's perspective, the journey takes approximately 25 years. But from the traveler's perspective, time dilation compresses this duration by a factor of 7. The subjective journey time drops to roughly 3.5 years. Push velocity to 99.9% of light speed, and the numbers become even more remarkable. Gamma at 22 compresses that same 25-year journey to barely over 1 year of subjective time. You could visit Vega and return before your second birthday aboard the ship. Earth would age 50 years during your round trip, but you would age only 2. The Pleiades star cluster, that famous grouping of hot blue stars visible in winter skies, lies approximately 440 light-years from Earth. At 99.99% of light speed, with gamma exceeding 70, the subjective journey time drops to approximately 6 years. The center of our galaxy lies approximately 26,000 light-years away. At 99.999% of light speed, with gamma exceeding 223, the subjective journey time falls to approximately 116 years. Still longer than a human lifetime, but within reach of a multi-generational crew. As an object accelerates, it gains kinetic energy. At low velocities, this follows familiar patterns. Doubling your velocity quadruples your kinetic energy. But as velocity approaches a significant fraction of light speed, something strange happens. The energy required to accelerate further begins climbing faster than expected. The object begins behaving as though it has more mass than it started with. At 50% of light speed, an object behaves as though it has about 15% more mass than it possesses at rest. At 90% of light speed, the effective mass has more than doubled. At 99%, the effective mass has increased by a factor of 7. Each increment of additional velocity requires not just more energy, but exponentially more energy. This mass increase explains why the speed of light represents an absolute barrier for any object possessing rest mass. As velocity approaches light speed, effective mass approaches infinity. Accelerating an infinite mass would require infinite energy. Since infinite energy does not exist, the final approach to light speed becomes asymptotic. You can get closer and closer, but you can never quite arrive. The practical energy requirements for relativistic travel are staggering. Consider accelerating a small probe, perhaps 1,000 kilograms, to 90% of light speed. The kinetic energy required exceeds 10 to the 19th joules. This equals the total energy output of our Sun for approximately 2 seconds, or the entire energy consumption of human civilization for roughly 1 million years, concentrated into accelerating a single small spacecraft. For a vessel capable of supporting human life, the mass might reach 100,000 kilograms or more. The energy requirement scales proportionally. These energy requirements explain why relativistic travel remains theoretical despite the physics being well understood for over a century. No propulsion system humanity has ever built, tested, or seriously proposed can deliver energy on these scales. Chemical rockets fall short by factors of billions. Nuclear fission improves the picture but remains inadequate. Even nuclear fusion, the process that powers the Sun, struggles to provide the energy density necessary. The twin paradox emerges naturally from these considerations. Imagine two identical twins, Alice and Bob. Alice boards a relativistic spacecraft and travels to a star 20 light-years distant at 90% of light speed. Bob remains on Earth. From Bob's perspective, Alice's outbound journey takes approximately 22 years. Her return journey takes another 22 years. Bob ages 44 years. From Alice's perspective aboard the spacecraft, time dilation compresses each leg of the journey. Her 22-year outbound journey feels like only 9.5 years. Her return journey feels like another 9.5 years. Alice experiences only 19 years of travel, while Bob experiences 44. When Alice returns to Earth, she is 19 years older than when she left. Bob is 44 years older. The twins, born on the same day, are now separated by 25 years of biological age. This scenario troubled early critics of relativity, who argued that motion is relative. The resolution lies in the asymmetry of their experiences. Alice experienced acceleration when her spacecraft changed velocity. Bob experienced no acceleration. This asymmetry determines who ages less. The twin paradox has been verified experimentally using precise atomic clocks. In 1971, physicists Joseph Haffel and Richard Keating flew cesium atomic clocks around the world on commercial airliners, comparing them to identical clocks that remained stationary. The flying clocks gained approximately 273 nanoseconds compared to the stationary clocks, exactly as relativity predicted. The effect was tiny because airplane velocities are tiny compared to light speed. But the effect was real and measurable. The visual experience of relativistic travel would be equally strange. Light arriving from ahead of the spacecraft becomes blue-shifted, its frequency increased by the Doppler effect. Stars ahead would shift from their normal colors toward blue, then ultraviolet, then X-ray frequencies as velocity increases. Light from behind experiences the opposite effect, becoming redshifted and stretched to longer wavelengths. Relativistic aberration further distorts the traveler's view. At 90% of light speed, most of the visible universe compresses into a circle spanning roughly 60 degrees ahead of the spacecraft. At 99%, this circle shrinks to approximately 16 degrees. At even higher velocities, the entire cosmos collapses into a brilliant point of light directly ahead, with darkness behind. The interstellar medium presents hazards that grow more severe with increasing velocity. Space between stars is not perfectly empty. Each cubic centimeter contains approximately one hydrogen atom on average. At low velocities, this material poses no threat. At relativistic velocities, this sparse material transforms into deadly radiation. Each hydrogen atom strikes the spacecraft with kinetic energy proportional to the gamma factor squared. At 90% of light speed, each impact delivers energy comparable to cosmic ray particles. At 99%, the energy increases by another factor of 20. Shielding against this radiation requires either massive physical barriers or active deflection systems. Despite these formidable challenges, the physics of relativistic travel remains clear and verified. Time dilation is not theoretical curiosity but measured phenomenon confirmed by decades of precision experiments. The equations permit human travel across interstellar and even intergalactic distances within a single biological lifetime. The barrier is not physics but propulsion technology. What technologies might actually achieve the velocities necessary? Nuclear pulse propulsion represents perhaps the most audacious concept ever seriously studied. The idea emerged in the late 1950s at General Atomics Laboratory in San Diego. Project Orion asked what seemed an insane question: what if you could harness nuclear explosions for spacecraft propulsion? The basic Orion concept works as follows. A spacecraft carries a large supply of nuclear explosive devices. These are ejected one at a time from the rear and detonated at a carefully calculated distance. The explosion creates a plasma fireball that expands outward. A massive pusher plate at the rear absorbs momentum from the fraction of plasma that strikes it, pushing the vessel forward. Shock absorbers smooth out the violent impulses into tolerable acceleration. The Project Orion team conducted actual tests using conventional explosives rather than nuclear devices. They built small models and detonated charges beneath them, demonstrating that the concept worked in practice. Nuclear test ban treaties halted the program in 1963, but the physics had been validated. Calculations showed that Orion could achieve performance far exceeding any other propulsion concept. A modest Orion using fission bombs could reach velocities of 3 to 4% of light speed. Larger designs incorporating fusion bombs could potentially achieve 8 to 10% of light speed. At 10% of light speed, the journey to a star 12 light-years distant would require roughly 120 years, still longer than a human lifetime but within range of multi-generational missions. The engineering challenges remain formidable but not insurmountable. The pusher plate must survive repeated exposure to nuclear fireballs at temperatures of millions of degrees. Material science has advanced considerably since the 1960s. Nuclear pulse propulsion requires no new physics and no materials beyond human capability. Antimatter propulsion occupies a unique position, offering energy density that dwarfs all other known fuel sources. When a particle of matter contacts its antimatter counterpart, both annihilate completely, converting 100% of their combined mass into energy. This compares to nuclear fission, which converts roughly 0.1% of mass to energy, and fusion, which achieves approximately 0.7%. Antimatter is roughly 140 times more energy-dense than fusion. A single gram of antimatter annihilating with a gram of normal matter releases approximately 180 trillion joules of energy, equivalent to the Hiroshima atomic bomb. The insurmountable obstacle lies in production. Antimatter does not exist naturally in significant quantities. Every antiproton must be manufactured through particle accelerator collisions requiring enormous energy inputs. current global antimatter production totals perhaps 10 to 20 nanograms per year. To appreciate how minuscule this is, reaching a star 10 light-years away with adequate antimatter would require accumulating current global production for approximately 5 billion years. The energy cost of creating antimatter through particle collisions consumes roughly 10 billion times more energy than the antimatter ultimately stores. Antimatter storage presents equally daunting challenges, requiring containment systems that suspend the fuel in perfect vacuum using magnetic fields. The longest antimatter has been successfully stored is approximately 16 hours, achieved in 2023. Scaling from 16 hours to decades represents an improvement factor of roughly 10,000. Beamed energy propulsion sidesteps the fundamental problem of carrying energy sources. The concept traces back to the 1960s when physicist Robert Forward proposed using powerful lasers to accelerate lightweight solar sails to interstellar velocities. Breakthrough Starshot, announced in 2016, represents the most serious modern effort. The project proposes using a ground-based laser array to accelerate tiny spacecraft to 20% of light speed. At this velocity, the journey to Alpha Centauri would require approximately 20 years. The concept envisions a phased array of lasers with combined power output approaching 100 gigawatts. This array would focus on a spacecraft consisting of a reflective sail measuring perhaps 4 meters across, connected to a tiny chip carrying instruments. The intense photon pressure would accelerate this vessel to 20% of light speed in approximately 10 minutes. The fatal limitation for human travel lies in deceleration. A laser-propelled sail accelerates by reflecting light from behind. It cannot slow down using the same mechanism because no laser exists at the destination. A breakthrough Starshot probe would flash through its target system at 20% of light speed, having mere minutes to conduct observations. For robotic probes this might suffice. For human travelers wishing to stop and explore, this approach fails completely. Fusion propulsion represents perhaps the most realistic path to velocities where time dilation becomes meaningful for human travelers. Fusion reactions combine light atomic nuclei, releasing energy far exceeding chemical or fission reactions. Project Daedalus, conducted by the British Interplanetary Society from 1973 to 1978, produced the most detailed engineering study of a fusion-powered interstellar probe. The design called for burning pellets of deuterium and helium-3 through inertial confinement fusion. Daedalus was designed to reach a star 6 light-years distant in approximately 50 years at 12% of light speed. At 15% of light speed, the journey to Sirius at 8.6 light-years would require approximately 57 years from Earth's perspective. Time dilation at this velocity compresses the traveler's experience by roughly 1%, providing minimal benefit. Hybrid concepts combining multiple technologies offer potential improvements. A spacecraft might use nuclear pulse propulsion for initial velocity, then deploy a magnetic sail to decelerate at the destination. Alternatively, a laser-boosted sail could provide initial acceleration with an onboard fusion drive handling deceleration. The realistic frontier for interstellar propulsion likely lies with advanced fusion systems, potentially augmented by beamed energy for initial acceleration. These technologies could plausibly achieve velocities of 15 to 20% of light speed within the coming century. At 20% of light speed, the time dilation benefit remains modest but measurable. The gamma factor at this velocity equals approximately 1.02, meaning 50 years of Earth time compressed to approximately 49 years of shipboard time. Achieving velocities where time dilation provides dramatic benefits, above 50% and ideally above 90% of light speed, requires propulsion advances that cannot currently be designed even on paper. The gap between 20% and 90% represents perhaps the most formidable barrier in propulsion physics. No known technology can bridge this gap. Yet the laws of physics do not prohibit relativistic travel. The equations permit velocities arbitrarily close to light speed, limited only by available energy. Given sufficient velocity, a human lifetime could span distances that light itself requires millennia or millions of years to traverse. Imagine a civilization where propulsion technology has become essentially perfect. Energy is unlimited. Acceleration to any desired velocity occurs routinely. Spacecraft achieve 99.999% of light speed. What then becomes the ultimate limit? The answer emerges not from engineering but from the structure of the universe itself. Even with perfect propulsion, cosmic geometry imposes boundaries that no technology can overcome. These boundaries are woven into the fabric of spacetime, encoded in the expansion of the cosmos. The observable universe extends approximately 46.5 billion light-years in every direction, with total diameter spanning roughly 93 billion light-years. Within this volume exist approximately 2 trillion galaxies. Yet the observable universe is not the same as the reachable universe. Light reaching Earth today from the most distant observable galaxies began its journey over 13 billion years ago. During that travel time, cosmic expansion stretched the space between those galaxies and Earth. Objects that emitted light 13 billion years ago now reside 46 billion light-years away. This expansion continues and accelerates. In 1998, 2 research teams studying distant supernovae discovered that the universe's expansion rate is increasing over time. This acceleration, driven by dark energy comprising approximately 68% of the universe's total energy content, means distant galaxies recede faster with each passing year. The discovery earned the 2011 Nobel Prize in Physics. Dark energy creates a boundary more fundamental than the observable horizon. The Hubble sphere marks the distance at which cosmic expansion equals the speed of light, approximately 14 billion light-years from Earth. Beyond this, galaxies recede faster than light, not through space but carried by expanding space itself. The cosmological event horizon defines the true boundary, currently approximately 16 to 17 billion light-years from Earth. This marks the maximum distance any signal or traveler departing today could ever reach, given infinite time and unlimited velocity. Beyond this boundary, space stretches faster than any approach velocity could overcome. Destinations beyond the event horizon are not merely difficult to reach but impossible by any means consistent with known physics. As dark energy continues accelerating expansion, the event horizon shrinks. Regions accessible today will become permanently inaccessible in the future. Within approximately 100 billion years, the event horizon will have contracted to encompass only our local group of galaxies. Within these cosmic constraints, what distances could a human lifetime span? At 99% of light speed, a traveler maintaining that velocity for 50 years of subjective time would cross approximately 350 light-years, encompassing perhaps 50,000 star systems. Push velocity to 99.9% and gamma exceeds 22. 50 years of shipboard time corresponds to over 1,100 years of Earth time. During those 50 subjective years, a traveler would cross approximately 1,100 light-years, encompassing millions of star systems. The Orion Nebula, one of the most spectacular star-forming regions, lies approximately 1,300 light-years distant. At 99.9% of light speed, a traveler could reach this cosmic nursery within a human lifetime. At 99.99%, gamma exceeds 70. The galactic center itself comes within reach. The supermassive black hole containing 4 million solar masses lies approximately 26,000 light-years from Earth. At 99.99% of light speed, a traveler could reach this in approximately 370 years of ship time. At 99.999%, gamma exceeds 223. 50 years of subjective time spans over 11,000 light-years. At 99.9999%, gamma exceeds 707. 50 subjective years would cross 35,000 light-years. A person could theoretically travel completely through our galaxy and experience the journey as lasting roughly 140 years of personal time. Push gamma into the thousands and intergalactic travel enters theoretical possibility. The Large Magellanic Cloud, a satellite galaxy, orbits approximately 160,000 light-years distant. At gamma equal to 3,200, a traveler could reach this in 50 years of ship time while Earth aged 160,000 years. The Andromeda Galaxy at 2.5 million light-years requires gamma equal to 50,000. 50 years of subjective travel would span this distance precisely. A traveler would emerge into an entirely separate island universe, impossibly distant from anything resembling home, having aged 50 years while Earth aged 2.5 million years. Push gamma higher still and the numbers become genuinely cosmological. The Virgo cluster, containing over 1,300 galaxies, approximately 54 million light-years distant, becomes theoretically accessible at gamma equal to 1,080,000. At the absolute extreme, where gamma approaches billions, the mathematics permits journeys spanning most of the observable universe within a single subjective lifetime. A traveler accelerating at 1 gravity continuously could theoretically reach the current observable horizon in approximately 45 years of ship time, while the universe aged roughly 28 billion years. Yet even these extreme calculations encounter the ultimate limit imposed by cosmic expansion. The event horizon cannot be crossed regardless of velocity. Destinations currently beyond approximately 17 billion light-years remain forever inaccessible. The one-way nature of extreme relativistic travel creates profound implications. Time dilation allows you to reach cosmic distances while aging minimally, but it does not allow return to the era you departed. Every journey becomes a journey forward through time from which no return is possible. Consider a round trip to the Pleiades at 440 light-years. At 99% of light speed, the outward journey would require approximately 445 years of Earth time, but only about 63 years of ship time. The return adds identical durations. The traveler would return to Earth having aged roughly 126 years, finding nearly 900 years had passed. The civilization that launched them would be ancient history. Extending round-trip distances multiplies this temporal isolation. A round trip to the galactic center at 99.99% would return a traveler to an Earth approximately 52,000 years in its future. A round trip to Andromeda would return them to an Earth 5 million years in its future. These calculations reveal that relativistic travel is fundamentally different from any transportation humanity has experienced. The voyages of exploration that shaped human history maintained connections between travelers and homes. Relativistic journeys sever those connections absolutely. A traveler departing Earth for distant stars accepts permanent exile not just from their home planet but from their entire historical era. They become time travelers moving only forward, unable to revisit the past they abandoned. For one-way travelers willing to abandon their past forever, the theoretical maximum encompasses nearly the entire observable universe. A lifetime measured in subjective decades could span distances of billions of light-years. For round-trip travelers hoping to maintain connection to human civilization, practical limits fall dramatically. Returning within a few centuries of Earth time constrains exploration to perhaps a few hundred light-years. This still encompasses hundreds of thousands of star systems, but represents a tiny fraction of the cosmic totality. The universe permits exploration on scales exceeding imagination. The laws of physics do not trap us in our solar system. They offer pathways to the stars, to other galaxies, to cosmic structures spanning billions of light-years. The barriers we face are technological, not physical. They represent our current inability to generate energies necessary for relativistic propulsion, not fundamental limits imposed by nature. Yet these same calculations reveal humanity's profound isolation. Even with perfect technology, most of the universe remains forever beyond reach. The event horizon recedes as we approach it. The overwhelming majority of galaxies we observe have already crossed beyond any possibility of contact. How far could a human actually travel in one lifetime? The answer depends on what we are willing to build, to sacrifice, to invest across generations. It depends on whether we value range over return, exploration over connection. It depends on choices that physics cannot make for us, choices that remain fundamentally human even when their consequences span cosmic distances. The stars are not impossibly distant. They merely wait for us to develop the means to reach them. Within the equations governing motion through spacetime lies a promise that distances measured in millions of light-years could someday fall within reach of a single human life. That promise is written in the mathematics of relativity, verified by a century of experiments, waiting for the engineering that would transform theoretical possibility into capability. The distance a human could travel in one lifetime is not ultimately limited by physics. It is limited by our determination and willingness to pay the price the universe demands for passage to the stars. If you found this exploration of actual physical limits fascinating, consider subscribing for more science-based content. Thanks for listening.